So we're going to talk about the common pathways for synthesis in the first year of your A-levels. So first of all, alkene to an alcohol to an aldehyde. Okay, there's your alkene. Want to go to an alcohol. The alcohol will be ethene to ethanol. How do you do that? Again, I'm stopping the video so you can actually just stop the video yourself and try and work it out for yourself. But here it is with H2O gas, steam, okay, and the acid H2SO4 or H3PO4. Now it's orange for a reason. Now if I go here and I go in this one, this is green for a reason. That's because the reaction to turn this from an alcohol to an aldehyde, okay, is done with H2, H plus Cr2O72 minus, and it's distilled, and that Cr2O72 minus is orange and it changes into green. And that's how you make an aldehyde. And that's probably one of the most common ones that you're going to come across, which is alkene to an alcohol to an aldehyde. Okay, so make sure that you can do that. Next one is alkene to dichloroalkane to dihydroxyalkane. Now, this one is for when you can see one functional group turning into two functional groups coming off it. Okay, so if you see two things added at the same time, this is how you do it. You do it with the dichloro and then you do it with the dihydroxy. So let's have a look at this. We've got the dichloro, okay, that's just done with chlorine. It's electrophilic addition and it's done with chlorine. It's an addition reaction. Now, next one, going to the alcohol. Well, that means chlorides changing into OHs. Chlorides changing into OHs is sodium hydroxide. So there you go. So you've got a two-stepper, hopefully straightforward for you. The more you practice these, the better you'll get. Now, alkene to carboxylic acid. So we've got an alkene. It's got to go to an alcohol before it goes to a carboxylic acid. So there's the alcohol again, and again, I've done it in orange. Hopefully you know why now. Okay, and that is going to go to your alcohol. Okay, what is missing? Let's write down what is missing. What do we think is missing here? Right, it is going to be, and I'm going to write it in this way now. I'm going to write it as steam, just to say you can put it as steam if you want. You don't have to put H2O gas. You can just put it as steam, and there you go. It goes to the alcohol, and then it goes to reflux, but this time it's a reflux instead of distill because we're making the carboxylic acid. So these little details make a huge amount of difference. And the reaction goes from orange to green. And that is your first few. But let's just get rid of this. Okay, and we've got rid of this and go to our next one. So our last common synthetic pathway is going to be bromoalkane to an alcohol to an alkene. So here's your bromoalkane, you want to make it into an alcohol. How do you do that? Well, you do that with sodium hydroxide, okay? Then alcohol to alkene, okay, is exactly the same reactants as you do with hydration to make an alcohol, but this time we're doing dehydration. We just don't add the steam, okay? We add the acid catalyst, which is H2SO4, H3PO4, and we make the alkene. So there are 4 common pathways which you need to know. So we're going to finish off this video with a combined analysis and synthesis question. We can't get all the question on one page, so we're going to show you a bit at a time. So we know it's a trans stereoisomer, okay, so that's important. Remember that for the future. We've got an elemental and a spectral analysis. Now the elemental analysis is on this page. So we've got the empirical formula percentages, so basically you do it. You stop the video, you do it. Okay, and there we have that, which then gives you your moles, which then you divide by the smallest number, which will give you your ratio. So you've got a ratio of C4H6O. Now that's our empirical formula to start off with. Let's bank that and look at the next part of the question. Okay, so we've got this empirical formula C4H6O, but they're giving us an infrared spectrum as well. So if you look at the infrared spectrum, we're looking at 2 areas. So the 2 areas are about 1750, okay, 1500 to about, 1620 to about 1750 or 1800. And we're looking for big peaks. Well, there's a big one right here. Then we're looking at 3000 to 3500, roughly speaking. We're looking for a big, kind of like a bowly type peak there. Okay, there's no bowly type peak, no big round one right there. That would say OH, this would say C double bond O. So therefore we've got a C double bond O but not a OH. These bits here are just CH bonds. Okay, so therefore there's our CO, and let's park that because we've got a bit of information. Okay, then we look at the mass spectrum. The mass spectrum has an M plus of 70. Now, important thing here is you look at other peaks sometimes as well, and this is why this is a hard question. So there's a peak right here. Now that peak right there is 41. Okay, that's 41. I've just gone down and said what it is. Now, the difference between 70 and 41 must be the other fragment. So we think this fragment is C3H5, because if you work it out, C3H5 adds to 41, and we just took it from there. Okay, so C3H5 makes sense, it's 41. Now, let's look at what that is. The difference between those two numbers is 29. Okay, so what I'm doing here is the mass spectrum. The peak with the greatest relative intensity is caused by loss of a functional group from the molecular ion of compound F. So molecular ion is 70. The big peak is 41, so the difference between them must be a fragment that we can identify. So let's do that, okay? And we've given you the answer there. That's the answer, but we'll go through that again. So m plus minus 41 gives 29. So we're looking for something that's 29, and we've colour-coded it there to help you out. 70 minus 41 is 29, okay? And we think that 41 is C3H5, which is the orange. If we look down here, this is the 29. You might ask, how did I get to that point? Because that's quite difficult. First of all, I knew it was a C double bond O, okay? And what you do is you find out what you do have, which we worked out that was C3H5, because 3 carbons and 5 hydrogens would work out. And all we have to do is that by trial and error, looking at the formula and saying what fits in there. Then it says here that what's left. And what's left, you can work out as 29, or 29, I've got to include the oxygen because I didn't include the oxygen here. I've got 1 leftover carbon, 1 leftover hydrogen. That's CHO. The only thing it can be is an aldehyde. Now the other thing is this. If you look here, you can see that this CH3 is pointing up and this CHO is pointing downwards. So we've got trans, or the hydrogens are pointing in opposite directions. So we've got trans, and that goes back to our trans stereoisomer right at the start. This is probably the most difficult one you'll get, I would imagine, at AS. Okay, and I hope I've explained it well. Good luck in your exams.